Welcome to week 6 of the problem solving session for the course Dynamical System and Control. So we'll start by revising the concepts that have been covered in the previous week. Okay, so in the previous problem solving session, we have gone through the qualitative analysis of the solution for a linear autonomous system of the form x dot equals to ax. So we have a system of the form x dot equals to ax, and let's quickly summarize the nature of the solution based on the eigenvalues of the system matrix A. So in the first case we have when both the eigenvalues are not equal, they are real and have same sign, and then if the sign is positive we have a unstable node, and when we have the sign negative then we have stable node. That means all the trajectories will converge towards the equilibrium point, which is 0 0 in this case, and obviously we are talking about second order system. And in the second case, when the eigenvalues are not equal, they are real but they have opposite sign, then we have solution of the nature saddle. And saddle means we have obviously one positive eigenvalue and one negative eigenvalue. That means the solution is going to be unstable. And in the third case, when we have complex eigenvalues with real part not equal to 0, in that case we have spiral, or we can call it focus. And in that, when we have, let's say the eigenvalues are of the form a plus minus ib, when we have real part greater than 0 then we have unstable focus, and when we have real part less than 0 means negative, we have a stable focus. And this also covers when we have equal eigenvalues, and then if they are negative then we have stable focus, and if they are positive then we have unstable focus, node. So when we have equal eigenvalues, in that case also we have, when the eigenvalues are negative we have stable node, and when they are positive we have unstable node. And finally, when the eigenvalues are purely imaginary, means when we have a equals to 0, then we have center. Okay, so this is all about the analysis of the solution in the phase plane, and we have categorized them as node, saddle, focus and center. Okay, then we started with the concept called limit cycle. So what is a limit cycle? So limit cycle we have defined again for a second order system. So we consider a system of the form x dot equals to f of xy and y dot equals to g of xy. Then the limit cycle is nothing but a closed curve of this system. Let's call this system 1. A limit cycle is a closed curve of system 1 such that the solution spiral into it or away from it as t goes to infinity. And if the solution spiral into it, then it is called, so we have a stable limit cycle. Stable limit cycle if all the solutions, obviously in the neighborhood to it. So if there is a limit cycle and if I start in the neighborhood of that limit cycle and I spiral into it, that means if all the solutions which are starting sufficiently close to that limit cycle spiral into it, then such limit cycles are called stable limit cycle. Otherwise, if it goes away from it, then it is an unstable limit cycle. Or let's say spiral away from it, we can say. Okay, so a limit cycle is basically a closed curve, means in the phase plane, if we have a phase plane x and y, the limit cycle will be a closed curve. And if any solution, if it starts nearby of that closed curve, then the limit cycle will be stable if the solution will spiral into it and stays on it. So that closed curve will be called a stable limit cycle. And okay, so that's about limit cycle. Next thing that is covered is about the Poincare-Bendixson criteria. Yeah, notes I will upload in the drive, so it will be uploaded today. Thank you for the reminder. Okay, so we will talk about Poincare-Bendixson non-existence theorem. Non-existence means the theorem which tells us what are the conditions on the system dynamics such that there is a guarantee that there will be no periodic orbit in the domain, whatever domain we are considering. So again, we will consider a second order system. Second order system we will consider, and let's focus on the domain D of the xy plane. So we are starting in the phase space, and we are interested in the region D, and we want to know, and we want to give a sufficient condition which tells us that if that condition is satisfied, then there will be no periodic orbit in the domain D. So what is that condition? So we will first fix the domain D of the xy plane, and obviously for existence and uniqueness we will consider f and g are continuous and they have uh, their partial derivative exist in that domain D. Then the system has no periodic orbit or solution in the domain D, and the condition is that the partial derivative of f with respect to x plus the partial derivative of g with respect to y has the same sign. Obviously in the domain D. So whatever domain we have considered, we will check that this partial derivative summation, if it has no sign change, then we will give guarantee that there exists no periodic solution or orbit in that domain D. Okay. And then, so based on the eigenvalues nature, we can analyze the stability of a linear autonomous system. And for a nonlinear system also, local behavior we can analyze based on the linearized system and analyzing its eigenvalues. But is there any other way that the stability of a general nonlinear system can be generalized, or we can give guarantee that the solution will converge to equilibrium point asymptotically, or whether it will not converge, it is unstable? So for that we have the Lyapunov theorem, or we can say Lyapunov stability analysis. So what it tests, it says that so we consider a general dynamical system of the form x dot equals to fx for non-autonomous system also. So for the cases when f is function of t and x also, Lyapunov function can be generalized, and that will be covered in future lectures. So first we will focus on a nonlinear autonomous system given as x dot equals to f of x. Then it says that if we construct a Lyapunov function v, and it is such that v should be positive definite, that means if we are analyzing stability about the equilibrium point, then it should be 0 at 0, and it should be greater than 0 for x belong to any domain D we are considering. So if we are analyzing stability in the domain D, then the Lyapunov function should be 0 at 0, and it should be positive for all values of x in the domain D. Then if we have constructed such Lyapunov function, then if the derivative v dot, or for this system how we can calculate its derivative, it is f into gradient of v. So that will be nothing but the derivative of v with respect to time. If this is less than equal to 0, that means if it is negative semi-definite, then the solution xt will be stable. Okay, and it will be asymptotically stable if this derivative of v is strictly negative definite. Obviously we are talking about in x belong to D but x not equal to 0. So we are excluding the equilibrium point. And when it is negative definite, then the solution will be asymptotically stable. Okay. So for the stable case, if I have constructed a Lyapunov function in the domain D which is positive definite, and if its derivative is negative semi-definite, then all my solution will stay in neighborhood of the origin, but that means the solution will be stable for all the trajectories starting in the domain D. And if I have constructed a Lyapunov function which is positive definite and its derivative is negative definite, obviously in x belong to D and x not equal to 0, just a minute. Okay. So when derivative of v with respect to time is negative definite in the region or in the domain D, then all the solution starting in the domain D will converge asymptotically to the equilibrium point, which is considered 0 in this case. Okay, so I think these are all the topics that have been covered in the last week. Now let's take up questions based on these. Okay, we have the first question. So we consider a second order system which is given as x1 dot is x2 and x2 dot equals to ax1 plus px2 minus x1 square x2 minus x1 cube, and let the domain of interest be the whole plane. So let D belong to R2. So we are interested in the whole state space. Then you have to tell me whether there exists any periodic solution or not in the domain D. There exists periodic orbit or not. Okay, how can we check whether there will be any periodic solution or not in the
That
domain D?
point care, whatever point care
Yes.
benedictions,
So we will
we
apply.
should do F by do X. And
So we will apply Poincare-Bendixson theorem, non-existence theorem, to check whether there exists any periodic solution or not. So for that we will have to find out the partial derivative of, so for here we have f as x2 and g as this term. Now we have to calculate del f upon del x1 plus del g upon del x2. So for del f upon del x1, so this will be 0, sorry. And then if we calculate del g upon del x2, it is b minus x1 square. Okay. And since we are interested in the whole phase space, means all the values of x1 and x2 in the R2 plane, so we have to check for all the real values for x1 and x2. Now we can see here that this thing will have no sign change in the domain D because it is only dependent on x1, and this term is always negative, minus x1 square. So the sign of this thing depends on the value of b. So if b is less than 0, then what we can conclude?
it will be always negative.
Then this term is always negative, means there will be no sign change throughout the domain D. And if there is no sign change throughout the domain D, then there will be no periodic solution in D. No periodic solution for X belong to D that we have considered. Okay. Okay, we have second question. Let's consider the second question. So, okay. Again we have a second order system. So consider x1 dot equals to minus x1 plus x1 cube plus x1 x2 whole square, and we have x2 dot as minus x2 plus x2 whole cube x1 square x2. For this system, show that no limit cycle exists. So for this system, we have to show that there is no limit cycle for this system. Okay, for this system, let's first see what are the equilibrium points for the given system. Now, if we see the equilibrium points, we can write system 1 as 1 minus, sorry, 1 minus x1 square and minus x2 square, and x2 dot we can have 1 minus x2 square and minus x1 square. So what are the equilibrium points for this system? Okay, so the equilibrium points for this system are 0, 0, and obviously we have set of equilibrium points that satisfy the condition x1 square plus x2 square equals to 1. Okay, so we have equilibrium point at 0, 0 and a continuum of equilibrium points given as x1 square plus x2 square equals to 1. That is all the points on the unit circle. I think this topic is not covered in the recorded lecture yet. So another theorem of Poincare-Bendixson, it states that there will exist a limit cycle only when there is no equilibrium point in that domain, and if there is an equilibrium point, then that is an unstable one. Okay, so if you check this equilibrium point and linearize the system, then you will find that this is a stable node. And since it is stable node, and then when you analyze the system on this domain, so when you consider a domain D, inside of this domain and outside of this domain, then you will figure out that every trajectory will starting inside this unit circle, will converge to 0 0, and every trajectory starting outside of this unit circle will go out. So the trajectories will not get trapped inside any domain D. So that will, in that way we can conclude that there will be no limit cycle for this system. But I think that criteria is not covered in the recorded lecture, so let's skip this question. Okay, consider a system given as we are considering a scalar system. So we have x dot equals to minus x minus 2x cube. So without finding the explicit solution for this system, that is without solving for solution, comment on the stability for this system. So how can we analyze? So we have a non-linear system given over here. So if it were a linear system, we can easily tell about the stability of the solution for this system. But since we have a non-linear system and we don't want to find out the solution, then how can we comment on the stability of the system?
Right now, ma'am.
Yes, so we will start with a Lyapunov function. So a Lyapunov function that we will consider, it should be a positive definite one. So the most common Lyapunov function that you will find out while solving any question or in the textbook is the quadratic form of Lyapunov function. So since it is a scalar system, we can start with half x square, and we will find out the derivative, which is given as f delta v, which is nothing but v dot. We are finding it like this because this is how it is given in the textbooks. So it is given as minus 2x cube into x, gradient of v is x, and it is minus x square minus 2x4. And so what we can tell about the derivative of v, is it negative definite? So this derivative of Lyapunov function is negative definite because this term is negative and it is 0 only when x is 0. So that means we have started with a positive definite Lyapunov function and we came across derivative of v which is negative definite, means it is negative in the whole region except at the origin. Because it is 0 only at the origin, that means the system will be asymptotically stable. It means that when we draw the solution xt with respect to time, in whatever initial condition we start, all will converge to 0 as t goes to infinity. Okay, and this you can also check by plotting in the MATLAB. So you can write this equation and solve it into using ODE, or you can use Simulink also, and then you can plot the trajectory with respect to time, and with different initial condition you will observe that the solution will converge to 0 as t goes to infinity. Okay, again let's consider a second order system. Okay, क्या हुआ? कौन है? क्या है? Comment on the stability of this system. नहीं खोल सकते हम. Okay, let's start with the Lyapunov function. Okay, if we consider a Lyapunov function, let's take up half x1 square plus half x2 square. What will be the derivative of v along the solution? So it will give us x1 x2 and then okay, when you see you can see that the derivative of v is such that we cannot comment anything about it, because we have this sign indefinite term x1 x2, and again we have this sign indefinite term x1 cube x2, and then we have x2 4. Then how can we proceed in order to analyze the stability of system? Because for this case we land up with sign indefinite terms for the derivative of v. Then how should we proceed? Okay, the only challenging thing for the Lyapunov analysis is on the selection of the Lyapunov function. So if we start with a Lyapunov function which is positive definite, and when we find out its derivative along the solution, then we get some terms which are sign indefinite, or we cannot tell anything about it. Does that mean that the system cannot be guaranteed to be stable or unstable? No, because the derivative of v depends on the choice of the Lyapunov function, and it is on us how good the Lyapunov function that we have considered, such that the derivative of v gives us uh, much more information about the stability. So for this case, if we consider this quadratic Lyapunov function, then we can see that this v dot gives us no such information that allow us to guarantee give any guarantee on the stability of system. But now if we change our selection of Lyapunov function, so let's suppose we consider the Lyapunov function as now this Lyapunov function is also positive definite, because this term is positive for whole of x1 and x2 belong to the R2 plane, and it is 0 only at x1 x2 equals to 0. Now along if we find out the derivative of v along the solution, then it will be x1 cube x1 dot plus x2 x2 dot, and then if I put x1, sorry, and x1 dot is nothing but x2, so it is x1 cube x2, and x2 dot is minus x1 cube minus x2 cube. So minus x1 cube minus x1 cube and minus x2 cube will give us x2 to the power 4. Now you can see that these two terms cancel out, and we have v dot equals to minus x2 4, and from here at least we can say that the system is going to be stable, because v dot is negative. But it is not negative definite, because we have v dot obviously is negative, but it is v dot is not 0 only at 0, because you can see that v dot will be 0 when x2 is equal to 0, but there is no information of x1. On what values of x1 this v dot will be 0, because v dot is a function of x2 only. Then in such cases we cannot say that v dot is negative definite, but at least we can say that v dot is negative semi definite. It is negative semi definite, and if derivative of v is negative semi definite, if v dot is negative semi definite, then what we can say about the stability of the system? The system is stable. Okay, for such cases when we have only partial information in the derivative of v, means if we cannot tell about the negative definiteness of the derivative of Lyapunov function, then there is another principle called the invariance principle, and that will be considered in the future lectures. So we add on invariance principle with the Lyapunov analysis to give guarantee on the asymptotic stability of the system. So that will be covered in the next lecture, I think. But for the time being, we can say that this system is stable. But for asymptotic stability, we have to work more on it. We have to apply invariance principle, and then we will check that this derivative of v will be 0 only at x1 0 and x2 0. Even if derivative of v is telling us that it is 0 at x2 equals to 0 and any value of x1, but there is a principle that allow us to tell that it is 0 only at x1 x2 equals to 0, and if that is the case, the system will be asymptotically stable. But that is left for future lectures. Okay, now let's move on to our next question. So consider a system given as -2 1 alpha 1 into x. So we have a linear autonomous system. Then we have to find condition such that the origin is saddle. We have to tell the system is saddle on what values of alpha. For saddle, what should be the nature of eigenvalues? For saddle, we know that the eigenvalues, if it is given as lambda 1 lambda 2, it should be real and it should have opposite sign. Okay, now since eigenvalues depend on the characteristic equation, so what will be the characteristic equation for this system? We have to work on the determinant of minus 2 minus lambda 1 alpha and 1 minus lambda. Okay, so this will give us the characteristic equation, and then we will have a quadratic equation in lambda, so it will be lambda square and minus 3 lambda minus 2 plus alpha I think it is plus lambda. Okay, so this will be the characteristic equation for this system, and from here for eigenvalues to be real and opposite, we can use the condition that this c by a, that is this term divided by this coefficient, should be less than 0. Okay, so let's impose that condition. So minus 2 plus alpha divided by this coefficient is 1, so it is this term only, and this should be less than 0. That means 2 plus alpha should be greater than 0, or alpha should be greater than minus 2. Okay, so for this system, if alpha is greater than minus 2, then the nature of eigenvalues will be real and of opposite signs. That means the solution is going to be saddle. And then what can we comment on the stability of the system? If we have saddle equilibrium point, solution will be stable or unstable?
Mm,
Yes,
unstable, no?
yes, the solution will be unstable because we have one eigenvalue as negative, which will try to stabilize the system, but at the same time we have one eigenvalue positive, which is sufficient enough to have unbounded solution. That is, uh, it will pull the solution away from the equilibrium point. So we have the, an unstable system. We have another system as x dot equals to x square minus x plus xy, and we have y dot as xy. Then for this system, we have to find out the equilibrium points and comment on their stability. Okay, let's see. The first equation can be written as x plus y minus 1, and y dot can be written as x into y. So the second equation will be 0 only when x equals to 0 or y equals to 0. So when x equals to 0, we have the equilibrium point for any value of y. So x equals to 0 means we have the equilibrium point 0 comma y, because when x equals to 0, both the dynamics will be exactly 0 on whatever value of y we can take. Okay, and when y equals to 0, what will be the value of, what should be the value of x? So when y equals to 0, we should have x equals to 1. So the another equilibrium point is 1 comma 0. So we have an infinite set of equilibrium point given as 1 comma 0 and a whole continuum of equilibria equilibria given as 0 comma y. Since we are interested in particular equilibrium point, so we will consider stability about 1 comma 0. So we will analyze stability about the equilibrium point given as 1 comma 0 for this system. So how we should proceed? Obviously we will linearize the system about this equilibrium point first. Now in order to linearize, we have to find out the Jacobian. So first let's find out its Jacobian. So let's write here only the Jacobian J. It is 2x minus 1 plus y, x, y and x. And we are interested at the point 1 comma 0. So the Jacobian at this point is 1 1 and 0. Okay, what are the equilibrium points for this system? For this matrix? Oh, sorry, what are the eigenvalues for this matrix? So we have repeated eigenvalues which is positive, given as 1. And since we have positive eigenvalues, that means the system will be unstable. So the trajectories which start in the neighborhood of the point 1 comma 0 will not be bounded. That means it will move away from the equilibrium point 1 comma 0. Every trajectory which starts in the neighborhood of 1 comma 0 will go away from it. And what if I start exactly at the point 1 comma 0? What happens if the trajectory starts exactly at the point 1 comma 0? Since it is an equilibrium point, so if I start exactly at the point 1 comma 0, I will remain there for all future time, because that's the definition of equilibrium point. If I start at the equilibrium point, that means the dynamics is 0 at that point. So I will not have any dynamics, I will stay there forever. So if I start exactly at the equilibrium point, I will remain there for all future time. But for this case, if I start in the neighborhood of this equilibrium point 1 comma 0, I will move away from it, because the eigenvalues at that equilibrium point are positive. Okay, we have system x dot equals to y plus x, and then we have y into so for this system we have to show that the system has limit cycle, and we have also identify the domain where the limit cycle will exist. So we have to check whether there will be a limit cycle or not, and if that exists, in what domain it will exist. So the system has limit cycle in the domain that we have to identify. Okay, in order to check the existence of limit cycle, let's start with a closed curve. So let's consider a curve given as x square plus y square equals to c. Okay, so this is obviously a closed curve whose radius depends on the parameter c, and let's check whether uh, how the solution of the system which is given using this differential equation behave when we consider the dynamics along any closed curve which is given as x square plus y square equals to c. So for that, let's consider the derivative of this closed curve. So let's consider half for easy evaluation of the derivative. So let's find out the derivative of the closed curve along the solution of the system. Okay, and what it will be? It will be x dot and y dot. Now when we put the dynamics in this equation, we will get y plus x 10 minus x square minus y square, and then we have y into, it is minus x minus y. Okay, so it will give us xy plus x square 10 minus x square minus y square, and then we have minus xy okay, so it is square plus y square minus 10, and these terms cancel out, and this can be written as, the minus will come out from here, so it will be x square plus y square, and then 10 minus, it will be 10 minus x square minus y square. So let's write it cleanly. So we have considered the derivative of the closed curve along the solution, and we come out with x square plus y square and 10 minus x square minus y square. Now based on this dynamics, what we can comment? Now if we see this dynamical equation, this term is always positive because it is quadratic, x square plus y square. What about this term, this second term? This second term will be positive when we have x square plus y square less than 10. So if we have x square plus y square less than 10, then this term or this whole term will be negative, and when x square plus y square is greater than 10, sorry, this will be positive. When we have x square plus y square greater than 10, then this whole term will be negative. So what does it mean? And at 10, at exactly 10, this derivative of x square plus y square will be exactly 0. So that means let's consider the phase plane. So we have x1 and we have x2. Okay. So we have considered a closed curve. We have considered this closed curve as x1 square plus y2 square equals to c. Okay. Now for this closed curve, along the solution of the system, we can see that the derivative of this will be 0 exactly when this closed curve is x square plus y square equals to 10. Okay, that means the solution will be stuck at this orbit when we have x1 square plus y square equals to 10, and when we have x1 square plus y1 square greater than 10. That means if I start outside this closed curve, how will the solution behave? It behaves such that its derivative is the derivative of the closed curve is positive. Sorry, it's negative. That means the closed curve radius will decrease. That means if I start outside this closed curve, I'm going to converge to this orbit given as x square plus y square equals to 10. And similarly, if I start inside means this thing. If I start inside this closed curve, then my radius will going to increase because I have a positive derivative. So my radius will going to increase in such a way that again I go to this orbit. Okay. So if I start outside this orbit, I will converge to this closed curve x square plus y square equals to 10. And also if I start inside of this, then again I am going to spiral out and then converge to this orbit. So that means we have a limit cycle in the domain which is given as x square plus, obviously we have to exclude origin equilibrium point because equilibrium point is the because 0 is the equilibrium point for this system. When we put x and y equals to 0, this derivative will be 0. So 0 is an equilibrium point for this system, so we must exclude equilibrium point. So the domain on which the limit cycle exists is from 0 to, so this is the domain, and the limit cycle is given as x square plus y square equals to 10. Okay. Okay, we'll stop here for today, and we have few more questions, but we will proceed with some more questions in the next lecture. So let's stop today. So thank you for joining.